हेलो एवरीवन, वंस अगेन वेलकम बैक टू आवर चैनल बीट द नीट। और आज मैं करने जा रही हूँ क्लास 11 थर्मोडायनेमिक्स ऑडियो बुक का पार्ट 2। इसका फर्स्ट पार्ट जिनके पास में नहीं है उसका लिंक मैंने डिस्क्रिप्शन में दे दिया है, तो वहां से जाकर के आप लोग देख सकते हैं। बाकी जो क्लास 11th क्लास 12th के केमिस्ट्री ऑडियो बुक की अलग अलग प्लेलिस्ट बनी हुई है, तो उम्मीद है कि आप लोगों के रिक्वेस्टेड चैप्टर्स आप लोगों के अकॉर्डिंग होते जा रहे हैं। जो बचे हुए 3-4 चैप्टर्स हैं जल्दी वो कंप्लीट करके आप लोगों को बायोलॉजी की तरह क्लास 11th और 12th की कंप्लीट एनसीईआरटी ऑडियो बुक प्रोवाइड कर दूंगी। सो चलिए टाइम वेस्ट नहीं करते हैं, थर्मोडायनेमिक्स का सेकंड पार्ट अपलोड करते हैं। और अगर ये वीडियोस आपको हेल्प करते हैं तो इसे प्लीज जरूर लाइक कीजिएगा, शेयर कीजिएगा, और अगर चैनल सब्सक्राइब नहीं है तो इसे सब्सक्राइब कर लीजिएगा। चलिए शुरू करते हैं। सी स्टैंडर्ड एंथैल्पी ऑफ फॉर्मेशन। The standard enthalpy change for the formation of 1 mole of a compound from its element in their most stable states of aggregation, also known as reference states, is called standard molar enthalpy of formation. Its symbol is delta FH, where the subscript F indicates that 1 mole of the compound in question has been formed in its standard state from its elements in their most stable states of aggregation. The reference state of an element is its most stable state of aggregation at 25 degrees Celsius and 1 bar pressure. For example, the reference state of dihydrogen is H2 gas and those of dioxygen, carbon and sulfur are O2 gas, C graphite and S rhombic respectively. Some reactions with the standard molar enthalpies of formation are as follows. H2O plus half O2 gives out H2O. Delta FH is equals to minus 285.8 kilojoule per mole. C plus 2H2 gives out CH4 and delta FH is equals to minus 74.81 kilojoule per mole. 2C plus 3H2 gives plus half O2 gives out C2H5OH. Delta FH is minus 277.7 kilojoule per mole. It is important to understand that a standard molar enthalpy of formation delta FH is just a special case of delta RH, where 1 mole of a compound is formed from its constituent elements, as in the above 3 equations where 1 mole of each water, methane and ethanol is formed. In contrast, the enthalpy change for an exothermic reaction CaO plus CO2 gives out CaCO3. Here delta RH is equals to minus 178.3 kilojoule per mole. Is not an enthalpy of formation of calcium carbonate, since calcium carbonate has been formed from other compounds and not from its constituent elements. Also, for the reaction given below, enthalpy change is not standard enthalpy of formation. Delta FH for HBr, H2 plus Br2 gives out 2HBr. Delta RH is equals to minus 178.3 kilojoule per mole. Here 2 moles instead of 1 mole of the product is formed from the elements, that is delta RH is equals to 2 delta FH. Therefore, by dividing all coefficients in the balanced equation by 2, expression for enthalpy of formation of HBr is written as half H2 plus half Br2 is equals to HBr. Delta FH is equals to minus 36.4 kilojoule per mole. Standard enthalpies of formation of some common substances are given in table 6.2. This is table 6.2. Here you can see the standard molar enthalpies of formation delta FH at 298 Kelvin of a few selected substances. There are so many, I can't read all of them. So better you just see this table here only. By convention, standard enthalpy for formation delta FH of an element in reference state, that is, its most stable state of aggregation, is taken as 0. Suppose you are a chemical engineer and want to know how much heat is required to decompose calcium carbonate to lime and carbon dioxide with all the substances in their standard state. CaCO3 gives out CaO plus CO2, and here the delta RH is unknown. Here we can make use of a standard enthalpy of formation and calculate the enthalpy change for the reaction. The following general equation can be used for enthalpy change calculation, and here is that equation. You can see this reaction for the products as well as for reactants, where A and B represent the coefficient of the products and reactants in the balanced equation. Let us apply the above equation for decomposition of calcium carbonate. Here coefficient A and B are 1 each. Therefore, delta RH is equals to delta FH is equals to CaO plus delta FH CO2 minus delta FH is equals to CaCO3. So the final value we will get here 178.3 kilojoule per mole. Thus, the decomposition of CaCO3 is an endothermic process and you have to heat it for getting the desired products. D. Thermochemical equations. A balanced chemical equation together with the value of its delta RH is called a thermochemical equation. We specify the physical state along with allotropic state of the substance in an equation. For example, C2H5OH plus 3O2 gives out 2CO2 plus 3H2O. Delta RH is equals to minus 1367 kilojoule per mole. The above equation describes the combustion of liquid ethanol at constant temperature and pressure. The negative sign of enthalpy change indicates that this is an exothermic reaction. It would be necessary to remember the following conventions regarding thermochemical equations. Number 1. The coefficients in a balanced thermochemical equation refer to the number of moles, never molecules of reactants and products involved in the reaction. Number 2. The numerical value of delta RH refers to the number of moles of substances specified by an equation. The standard enthalpy change delta RH will have units as kilojoule per mole. To illustrate the concept, let us consider the calculation of heat of reaction for the following reaction. Fe2O3 plus 3H2 gives out 2Fe plus 3H2O. And from the table 6.2 of a standard enthalpy of formation, we will find here you can see the complete calculation and the final value of delta FH1 we will get here minus 33.3 kilojoule per mole. Note that the coefficient used in these calculations are pure numbers which are equal to the respective stoichiometric coefficients. The unit for delta RH is kilojoule per mole, which means per mole of reaction. Once we balance the chemical equation in a particular way as above, this defines the mole of reaction. If we had balanced the equation differently, for example, half Fe2O3 plus 3 by 2 H2 gives out Fe plus 3 by 2 H2O. Then this amount of reaction would be 1 mole of reaction and delta RH would be minus 16.6 kilojoule per mole. That is half of delta RH1. It shows that enthalpy is an extensive quantity. Number 3, when a chemical equation is reversed, the value of delta RH is reversed in sign. For example, N2 plus 3H2 gives out 2NH3 and here delta RH is equals to minus 91.8 kilojoule per mole and 2NH3 gives out N2 plus 3H2 and here the delta RH is equals to plus 91.8 kilojoule per mole. E. Hess Law of constant heat summation. We know that enthalpy is a state function. Therefore, the change in enthalpy is independent of the path between initial state, that is reactants, and final state products. In other words, enthalpy change for a reaction is the same whether it occurs in one step or in a series of steps. This may be stated as follows in the form of Hess Law. If a reaction takes place in several steps, then its standard reaction enthalpy is the sum of standard enthalpies of the intermediate reactions into which the overall reaction may be divided at the same temperature. Let us understand the importance of this law with the help of an example. Consider the enthalpy change for the reaction C graphite plus 1 by 2 O2 gives out CO delta RH. Although CO is a major product, some CO2 gas is always produced in this reaction. Therefore, we cannot measure enthalpy change for the above reaction directly. However, if we can find some other reactions involving related species, it is possible to calculate the enthalpy change for the above reaction. Let us consider the following reactions. C graphite plus O2 gives out CO2. Delta RH is equals to minus 393.5 kilojoule per mole. And here CO plus half O2 gives out CO2 and here it is delta RH is minus 283.0 kilojoule per mole. We can combine the above two reactions in such a way so as to obtain the desired reaction. To get 1 mole of CO on the right, we reverse equation second. In this, heat is absorbed instead of being released. So we change sign of delta RH value. CO2 gives out CO plus half O2 and here the value of delta RH is equals to plus 283.0 kilojoule per mole. Adding equation 1 and 3rd, we get the desired equation. C plus half O2 gives out CO, and the value of delta RH is equals to minus 110.5 kilojoule per mole. In general, if enthalpy of an overall reaction A gives out B along one route is delta RH and delta RH1, delta RH2 and delta RH3 representing enthalpies of reactions leading to the same product. B along another route, then we have delta RH is equals to delta RH1, delta RH2 and so on. It can be represented as, here you can see this, 6.5 enthalpies for different types of reaction. It is convenient to give name to enthalpy specifying the types of reactions. A. Standard enthalpy of combustion, symbol delta CH. Combustion reactions are exothermic in nature. These are important in industry, rocketry, and other walks of life. A standard enthalpy of combustion is defined as the enthalpy change per mole of a substance when it undergoes combustion and all the reactants and products being in their standard states at the specified temperature. Cooking gas in cylinders contain mostly butane, C4H10. During complete combustion of 1 mole of butane, 2658 kJ of heat is released. We can write the thermochemical reaction for this as C4H10 plus 13 by 2 O2 gives out 4CO2 plus 5H2O. Here the delta CH is equals to minus 2658.0 kJ per mole. Similarly, combustion of glucose gives out 2802.0 kJ. It means the 2802.0 kJ per mole of heat, for which the overall equation is C6H12O6 plus 6O2 gives out 6CO2 plus 6H2O, and the delta CH is equals to minus 2802.0 kJ per mole. Our body also generates energy from food by the same overall process as combustion, although the final products are produced after a series of complex or biochemical reactions involving enzymes. The problem 6.9 you can see here. B. Enthalpy of atomization, symbol delta AH. Consider the following example of atomization of dihydrogen. H2 gives out 2H, and here the delta AH is equals to 435.0 kJ per mole. You can see that H atoms are formed by breaking HH bond in dihydrogen. The enthalpy change in this process is known as enthalpy of atomization. Delta AH. It is the enthalpy change on breaking 1 mole of bonds completely to obtain atoms in the gas phase. In case of diatomic molecules like dihydrogen, the enthalpy of atomization is also the bond dissociation enthalpy. The other examples of enthalpy of atomization can be CH4 gives out C plus 4H, and here the delta AH value is 1665 kJ per mole. Note that the products are only atoms of carbon and hydrogen in gaseous phase. Now see the following reaction. Sodium gives out sodium, and here the solid is converting into the gaseous form. So it means the delta AH is equals to 108.4 kJ per mole. In this case, the enthalpy of atomization is same as the enthalpy of sublimation. C. Bond enthalpy, symbol is delta bond H. Chemical reactions involve the breaking and making of chemical bonds. Energy required to break a bond and energy is released when a bond is formed. It is possible to relate heat of reaction to changes in energy associated with breaking and making of chemical bonds. With reference to the enthalpy changes associated with chemical bonds, two different terms are used in thermodynamics. Number 1, bond dissociation enthalpy. Number 2, mean bond enthalpy. Let us discuss these terms with reference to diatomic and polyatomic molecules. Diatomic molecules, consider the following processes in which the bonds in 1 mole of dihydrogen gas are broken. H2 gives out 2H, and here the delta HH bond H enthalpy is equals to 435.0 kJ per mole. The enthalpy change involved in this process is the bond dissociation enthalpy of HH bond, and the bond dissociation enthalpy is the change in enthalpy when 1 mole of covalent bonds of a gaseous covalent compound is broken to form products in the gas phase. Note that it is the same as the enthalpy of atomization of dihydrogen. This is true for all diatomic molecules. For example, Cl2 gives out 2Cl, and here the delta H value is 242 kJ per mole, and for O2 gives out 2O, and here the delta O double bond OH is equals to 428 kJ per mole. In the case of polyatomic molecules, bond dissociation enthalpy is different from different bonds within the same molecule. Polyatomic molecules. Let us now consider a polyatomic molecule like methane, CH4. The overall thermochemical equation for its atomization reaction is given below. CH4 gives out C plus 4H. Here the delta AH is equals to 1665 kilojoule per mole. In methane, all the 4 carbon-hydrogen bonds are identical in bond length and energy. However, the energies required to break the individual CH bonds in each successive step differ. See all these steps. In the first step, when the CH4 is breaking down into the CH3 plus hydrogen, so delta H value is equals to 427 kilojoule per mole. In the next step, when CH3 is converting into the CH2 plus hydrogen, the delta H value is 439 kilojoule per mole. When CH2 is breaking down into the CH plus H, the delta H value is equals to plus 452 kilojoule per mole. And when the CH is breaking down into the carbon plus hydrogen, then its delta H value is 347 kilojoule per mole. Therefore, CH4 gives out C plus 4H and the delta H is 1665 kilojoule per mole. In such cases, we use mean bond enthalpy of CH bond. And for example, in CH4, the delta CHH is calculated as the final value we will get here, the 416 kilojoule per mole. We find that mean CH bond enthalpy in methane is 416 kilojoule per mole. It has been found that mean CH bond enthalpies differ slightly from compound to compound, as in CH3, CH2, Cl, CH3, NO2, etc. But it does not differ in a great deal. Using Hess Law, bond enthalpies can be calculated. Bond enthalpy value of some single and multiple bonds are given in table 6.3. The reaction enthalpies are very important quantities, as these arise from the changes that accompany the breaking of old bonds and formation of the new bonds. We can predict enthalpy of a reaction in gas phase if we know different bond enthalpies. The standard enthalpy of reaction delta RH is related to bond enthalpies of the reactants and products in gas phase reactions. So here you can see the delta RH is equals to summation of bond enthalpies of reactants minus the summation of bond enthalpies of the product. This relationship is particularly more useful when the required value of delta FH are not available. The net enthalpy change of a reaction is the amount of energy required to break all the bonds in the reactant molecules minus the amount of energy required to break all the bonds in the product molecules. Remember that this relationship is approximate and is valid when all substances, that is reactants and products in the reactions, are in gaseous state. Now see the table 6.3a, some mean single bond enthalpies in kilojoule per mole at 298 Kelvin. And in table 6.3, the same mean multiple bond enthalpies in kilojoule per mole at 298 Kelvin. D. Lattice enthalpy. The lattice enthalpy of an anionic compound is the enthalpy change which occurs when 1 mole of an anionic compound dissociates into its ions in gaseous state. NaCl gives out Na positive plus Cl negative, and here the delta lattice H is equals to plus 788 kilojoule per mole. Since it is impossible to determine lattice enthalpies directly by experiment, we use an indirect method where we construct an enthalpy diagram called a bond-Haber cycle. Let us now calculate the lattice enthalpy of NaCl by following the steps given below. Na gives out solid to gaseous Na, sublimation of sodium metal. Here the delta sublimation H is equals to 108.4 kilojoule per mole. See this enthalpy diagram for lattice enthalpy of NaCl. Number 2. Na gaseous gives out Na ion plus 1 electron. The ionization of sodium atoms, ionization enthalpy, and the value is 496 kilojoule per mole. Number 3, half Cl2 gives out Cl. The dissociation of chlorine, the reaction enthalpy is half the bond dissociation enthalpy, and that is equivalent to 121 kilojoule per mole. Number 4, Cl plus 1 electron gives out Cl negative. And electron gained by chlorine atom, the electron gain enthalpy is equals to minus 348.6 kilojoule per mole. You have learnt about ionization enthalpy and electron gain enthalpy in Unit 3. In fact, these terms have been taken from thermodynamics. Earlier terms, ionization energy and electron affinity, were in practice in place of the above terms. And now I am reading the ionization energy and electron affinity. The ionization energy and electron affinity are defined at absolute zero. At any other temperature, heat capacities for the reactants and the products have to be taken into account. Enthalpies of reactions for M gaseous form converted into the M positive plus 1 electron for ionization, and M plus 1 electron gives out M negative for electron gain at temperature T is equals to, and here you can see the complete reaction. Therefore, delta RH is equals to E naught plus 5 by 2 RT, and delta RH electron gain enthalpy is equals to minus A minus 5 by 2 RT. Number 5, Na positive plus Cl negative gives out NaCl. The sequence of a step is shown in the figure 6.9, the diagram here, and is known as Born-Haber cycle. See this cycle again. Importance of the cycle is that the sum of the enthalpy change around a cycle is zero. Applying Hess's law, we get the delta lattice H value is equals to 788 kilojoule. For NaCl, internal energy is smaller by 2 RT because 2 delta Ng is equals to 2 and is equal to plus 783 kilojoule per mole. Now we use the value of lattice enthalpy to calculate enthalpy of solution. From the expression, the delta solution H is equals to delta lattice H plus delta hydration H. For 1 mole of NaCl, the lattice enthalpy is equals to plus 788 kilojoule per mole, and delta hydration H is equals to minus 784 kilojoule per mole from the literature. And the final value delta sol H we will get here the plus 4 kilojoule per mole. The dissolution of NaCl is accompanied by very little heat change. E. Enthalpy of solution. Enthalpy of solution of a substance is the enthalpy change when 1 mole of it dissolves in a specified amount of solvent. The enthalpy of solution at infinite dilution is the enthalpy change observed on dissolving the substance in an infinite amount of solvent when the interaction between the ions or solute molecules are negligible. When an ionic compound dissolves in a solvent, the ions leave their ordered positions on the crystal lattice. These are now more free in solution, but solvation of these ions, hydration in case solvent is water, also occurs at the same time. This is shown diagrammatically for an ionic compound AB. See this. The enthalpy of solution of AB delta solution H in water is therefore determined by the selective values of the lattice enthalpy delta lattice H and enthalpy of hydration of ion delta hydration H as delta solution H is equals to delta lattice H plus delta hydration H. For most of ionic compounds, delta solution H is positive and the dissociation process is endothermic. Therefore, the solubility of the most salt in water increases with rise of temperature. If the lattice energy is very high, the dissolution of the compound may not take place at all. Why do many fluorides tend to be less soluble than the corresponding chlorides? Estimates of the magnitudes of enthalpy change may be made by using tables of bond energies, enthalpies, and lattice energy enthalpies. F. Enthalpy of dilution. It is known that the enthalpy of solution is the enthalpy change associated with the addition of a specified amount of solute to specified amount of solvent at a constant temperature and pressure. This argument can be applied to any solvent with slight modification. Enthalpy change for dissolving 1 mole of gaseous hydrogen fluoride in 10 mole of water can be represented by the following equation. For convenience, we will use the symbol aqueous for water. HCl plus 10 aqueous equals to HCl multiplied by 10. Delta H value is minus 69.01 kilojoule per mole. Let us consider the following set of enthalpy changes here. The HCl plus 25 aqueous, that is the value of delta H is here minus 72.03 kilojoule per mole, and HCl plus 40 aqueous, so HCl into 40 aqueous, delta H value is minus 72.79 kilojoule per mole. HCl plus infinite aqueous, the HCl into infinite aqueous, and the delta H value is minus 74.85 kilojoule per mole. The values of delta H show general dependence of the enthalpy of solution on amount of solvent. As more and more solvent is used, the enthalpy of solution approaches a limiting value. That is the value in infinite dilute solution. For hydrochloric acid, the value of delta H is given above in equation S3, and here is the equation S3. If we subtract the first equation from the second equation, that is S2, in the above set of equation, we will obtain the final delta H value is here minus 0.76 kilojoule per mole. This value of delta H is enthalpy of dilution. It is of the heat withdrawn from the surroundings when additional solvent is added to the solution. The enthalpy of dilution of a solution is dependent on the original concentration of the solution and the amount of solvent added. 6.6 is spontaneity. The first law of thermodynamics tells us about the relationship between the heat absorbed and the work performed on or by a system. It puts no restrictions on the direction of heat flow. However, the flow of heat is unidirectional from higher temperature to lower temperature. In fact, all naturally occurring processes, whether chemical or physical, will tend to proceed spontaneously in one direction only. For example, a gas expanding to fill the available volume, burning carbon and dihydrogen giving carbon dioxide. But heat will not flow from cooler body to warmer body on its own. The gas in a container will not spontaneously contract into one corner, or carbon dioxide will not form carbon and dioxygen spontaneously. These and many other spontaneously occurring changes show unidirectional change. We may ask, what is the driving force of a spontaneously occurring changes? What determines the direction of a spontaneous change? In this section, we shall establish some criteria for these processes, whether these will take place or not. Let us first understand what do we mean by spontaneous reaction or change. You may think by your common observation that spontaneous reaction is one which occurs immediately when contact is made between the reactants. Take the case of combination of hydrogen and oxygen. These gases may be mixed at room temperature and left for many years without observing any perceptible change, although the reaction is taking place between them. It is at an extremely slow rate. It is still called spontaneous reaction. So spontaneity means having the potential to proceed without the assistance of external agency. However, it does not tell about the rate of reaction of the process. Another aspect of a spontaneous reaction or process, as we see, is that these cannot reverse their direction on their own. We may summarize it as follows. A spontaneous process is an irreversible process and may only be reversed by some external agency. A. Is decrease in enthalpy a criteria for spontaneity? If we examine the phenomena like flow of water downhill or fall of a stone onto the ground, we find that there is a net decrease in potential energy in the direction of change. By analogy, we may be tempted to state that a chemical reaction is spontaneous in a given direction because decrease in energy has taken place, as in the case of exothermic reaction. For example, half N2 plus 3 by 2 H2 gives out NH3. Delta RH value is minus 46.1 kilojoule per mole. Half H2 plus half Cl2 gives out HCl. Delta RH value is minus 92.32 kilojoule per mole. H2 plus half O2 gives out H2O. Delta RH value is equals to minus 285.8 kilojoule per mole. The decrease in enthalpy in passing from reactants to product may be shown for any exothermic reaction on an enthalpy diagram as shown in figure 6.10a. Thus, the postulates that driving force for a chemical reaction may be due to the decrease in energy sounds reasonable as the basis of evidence so far. Now, let us examine the following reactions. Half N2 plus O2 gives out NO2 and the delta RH is plus 33.2 kilojoule per mole. C plus 2S gives out CS2 and the delta RH value is plus 128.5 kilojoule per mole. Figure 6.10a enthalpy diagram for exothermic reactions. These reactions, though endothermic, are spontaneous. The increase in enthalpy may be represented on an enthalpy diagram as shown in figure 6.10b. Figure 6.10b enthalpy diagram for endothermic reaction. Therefore, it becomes obvious that while decrease in enthalpy may be a contributory factor for spontaneity, but it is not true for all cases. B. Entropy and spontaneity. Then what drives the spontaneous process in a given direction? Let us examine such a case in which delta H is equals to 0. That is, there is no change in enthalpy, but still the process is spontaneous. Let us consider diffusion of two gases into each other in a closed container which is isolated from the surrounding as shown in figure 6.11. The two gases, say gas A and gas B, are represented by black dots and white dots respectively. Here 6.11 diagram, diffusion of two gases, and separated by a movable partition. When the partition is withdrawn, that is in 6.11b, and the gases begin to diffuse into each other, and after a period of time diffusion will be complete. Here you can see the board diagram A and B. Let us examine the process before partition. If we were to pick up the gas molecules from left container, we would be sure that these will be molecules of gas A, and similarly if we were to pick up the gas molecules from right container, we would be sure that these molecules will be molecules of gas B. But if we were to pick up molecules from container when partition is removed, we are not sure whether the molecules picked are of gas A or gas B. We say that the system has become less predictable or more chaotic. We may now formulate another postulate. In an isolated system, there is always a tendency for the system's energy to become more disordered or chaotic, and this could be a criteria for spontaneous change. At this point, we introduce another thermodynamic function, entropy, denoted as S. The above mentioned disorder is the manifestation of entropy. To form a mental picture, one can think of entropy as a measure of the degree of randomness or disorder in the system. The greater the disorder in an isolated system, the higher is the entropy. As far as a chemical reaction is concerned, this entropy change can be attributed to rearrangement of atoms or ions from one pattern in the reactants to another in the products. If the structure of the product is very much disordered than that of reactants, there will be a resultant increase in entropy. The change in entropy accompanying a chemical reaction may be estimated qualitatively by a consideration of the structures of a species taking part in the reaction. Decrease of regularity in a structure would mean increase in entropy for a given substance. The crystalline solid state is the state of lowest entropy, most ordered, and the gaseous state is a state of highest entropy. Now let us try to quantify entropy. One way to calculate the degree of disorder or chaotic distribution of energy among molecules would be through statistical method, which is beyond the scope of this treatment. Other way would be to relate this process to the heat involved in a process, which would make entropy a thermodynamic concept. Entropy, like any other thermodynamic property such as internal energy U and enthalpy H, is a state function, and delta S is independent of path. Whenever heat is added to the system, it increases molecular motions, causing increased randomness of the system. Thus, heat has randomizing influence on the system. Can we equate delta S with Q? Wait. Experience suggests us that the distribution of heat also depends on the temperature at which heat is added to the system. A system at higher temperature has greater randomness in it than one at lower temperature. Thus, temperature is the measure of average chaotic motion of particles in the system. Heat added to a system at lower temperature causes greater randomness than when the same quantity of heat is added to at higher temperature. This suggests that the entropy change is inversely proportional to the temperature. Delta S is related with Q and T for a reversible reaction as delta S is equals to Q reversible upon T. The total entropy change, delta S total, for the system and surrounding of a spontaneous process is given by delta S total, delta S system, and delta S surrounding is greater than 0. When a system is in equilibrium, the entropy is maximum and the change in entropy delta S is equals to 0. We can say that entropy for a spontaneous process increases till it reaches maximum, and at equilibrium the change in entropy is 0. Since entropy is a state property, we can calculate the change in entropy of a reversible process by delta S system equal to Q system reversible upon T. We find that both the reversible and irreversible expansion for an ideal gas under isothermal condition, delta U is equals to 0. But delta S total, that is delta S system plus delta S surrounding, is not 0 for irreversible process. Thus, delta U does not discriminate between reversible and irreversible processes, whereas delta S does. C. Gibbs energy and spontaneity. We have seen that for a system, it is the total entropy change, delta S total, which decides the spontaneity of the process. But most of the chemical reactions fall into the category of either closed system or open systems. Therefore, for most of the chemical reactions, there are changes in both enthalpy and entropy. It is clear from the discussion in previous sections that neither decrease in enthalpy nor increase in entropy alone can determine the direction of spontaneous change for these systems. For this purpose, we define a new thermodynamic function, the Gibbs energy or Gibbs function G. G is equals to H minus Ts. Gibbs function G is an extensive property and a state function. The change in Gibbs energy for the system, delta G system, can be written as Delta G system is equals to delta H system minus T delta S system minus S system delta T. At constant temperature, delta T is equals to 0. Delta G system is equals to delta H system minus T delta S system. Usually the subscript system is dropped and we simply write this equation as delta G is equals to delta H minus T delta S. Thus gives energy change, enthalpy change minus temperature into entropy change, that is equivalent to the Gibbs energy change and is referred to as the Gibbs equation, one of the most important equation in chemistry. Here we have considered both terms together for spontaneity, energy in terms of delta H, and entropy delta S, a measure of disorder, as indicated earlier. Dimensionally, if we analyze, we find the delta G has units of energy because both delta H and the T delta S are energy terms, since T delta S is equals to K, J upon K is equals to J, Joule. Now let us consider delta G is related to the reaction spontaneity. We know delta S total is equals to delta S system plus delta S surrounding. If the system is in thermal equilibrium with the surrounding, then the temperature of the surrounding is the same as that of the system. Also, increase in enthalpy of the surrounding is equal to decrease in enthalpy of the system. Therefore, entropy change of surroundings, delta S surrounding is equals to delta H surrounding upon T is equals to minus delta H system upon T. So, delta S total is equals to delta S system plus in bracket minus delta H system upon T. After rearranging the above equation, we are having T delta S total is equals to T delta S system minus delta H system. And for spontaneous process, S delta S total is greater than 0. So, T delta S system is minus delta H system is greater than 0. So, the final we are having the negative in bracket delta H system minus T delta S system is greater than 0. Using equation 6.21, the above equation can be written as minus delta G is greater than 0. So, delta G is equals to delta H minus T delta S is less than 0. Delta H system is the enthalpy change of a reaction. T delta S system is the energy which is not available to do useful work. So, delta G is the net energy available to do useful work and is thus a measure of the free energy. For this reason, it is also known as the free energy of the reaction. Delta G gives a criteria for spontaneity at constant pressure and temperature. Number 1, delta G is negative. If then it means it is less than 0. The process is spontaneous. Number 2, if delta G is positive, it means greater than 0. The process is non-spontaneous. Note, if a reaction has a positive enthalpy change and positive entropy change, it can be spontaneous when T delta S is large enough to outweigh delta H. This can happen in two ways. A, the positive entropy change of the system can be small, in which case T must be large. B, the positive entropy change of the system can be large, in which case T may be small. The former is one of the reasons why reactions are often carried out at high temperature. Table 6.4 summarizes the effect of temperature on the spontaneity of reactions. D, entropy and second law of thermodynamics. We know that for an isolated system, the change in energy remains constant. Therefore, increase in entropy in such system is the natural direction of spontaneous change. This is in fact the second law of thermodynamics. Like first law of thermodynamics, second law can also be stated in several ways. The second law of thermodynamics explains why spontaneous exothermic reactions are so common. In exothermic reactions, heat released by the reaction increases the disorder of the surroundings and overall entropy change is positive, which makes the reaction spontaneous. E, absolute entropy and third law of thermodynamics. Molecules of a substances may move in a straight line in any direction. They may spin like a top and the bonds in the molecules may stretch and compress. These motions of the molecule are called translational, rotational and vibrational motion respectively. When temperature of the system rises, these motions become more vigorous and entropy increases. On the other hand, when temperature is lowered, the entropy decreases. The entropy of any pure crystalline substance approaches zero as the temperature approaches absolute zero. This is called third law of thermodynamics. This is so because there is a perfect order in a crystal at absolute zero. The statement is confined to pure crystalline solid because theoretical arguments and practical evidences have shown that entropy of a solution and supercooled liquid is not zero at 0K. The importance of third law lies in the fact that it permits the calculation of absolute values of entropy of a pure substance from thermal data alone. For a pure substance, this can be done by summing Q reversible upon T increments from 0 Kelvin to 298 Kelvin. Standard entropies can be used to calculate standard entropy changes by a Hess Law type of calculation. 6.7 gives energy change and equilibrium. We have seen how a knowledge of the sign and magnitude of the free energy change of chemical reaction allows. Number 1. Prediction of the spontaneity of the chemical reaction. Number 2. Prediction of the useful work that could be extracted from it. So far we have considered free energy changes in irreversible reactions. Let us now examine the free energy changes in reversible reactions. Reversible under strict thermodynamic sense is a special way of carrying out a process such that system is at all times in perfect equilibrium with its surroundings. When applied to a chemical reaction, the term reversible indicates that a given reaction can proceed in either direction simultaneously so that a dynamic equilibrium is set up. This means that the reaction in both the directions should proceed with a decrease in free energy, which seems impossible. It is possible only if at equilibrium the free energy of the system is minimum. If it is not, the system would spontaneously change to configuration of lower free energy. So the criteria for equilibrium A plus B reversible C plus D is delta Rg is equals to 0. Gives energy for a reaction in which all reactants and products are in a standard state. Delta Rg is related to the equilibrium constant of the reaction as follows. So 0 is equals to delta Rg plus Rt ln K, and delta Rg is equals to minus Rt ln K, and delta Rg is equals to minus 2.303 Rt log K. We also know that delta Rg is equals to delta Rh minus T delta Rs is equals to minus Rt ln K. For strongly endothermic reactions, the value of delta Rh may be large and positive. In such a case, value of K will be much smaller than 1 and the reaction is unlikely to form much product. In case of exothermic reaction, delta Rh is large and negative and delta Rh is likely to be large and negative too. In such cases, K will be much larger than 1. We may expect strongly exothermic reactions to have a large K and hence can go to near completion. Delta Rg also depends upon delta Rs if the changes in the entropy of reaction is also taken into account. The value of K or extent of chemical reaction will also be affected. Table 6.4 Effect of temperature on spontaneity of the reaction. The term low temperature and high temperature are relative for a particular reaction. High temperature could even mean room temperature, depending on whether delta Rs is positive or negative. Using equation 6.24, number 1, it is possible to obtain an estimate of delta G from the measurement of delta H and delta S and then calculate K at any temperature for economic yields of the product. Number 2, if K is measured directly in the laboratory, value of delta G at any other temperature can be calculated using equation 6.24. Summary. Thermodynamics deals with energy change in chemical or physical processes and enable us to study these changes quantitatively and to make useful predictions. For these purposes, we divide the universe into the system and the surroundings. Chemical or physical processes lead to evolution for absorption of heat, part of which may be converted into work. These quantities are related through the first law of thermodynamics via delta U is equals to Q plus W. Delta U change in internal energy depends on initial and final states only and is a state function, whereas Q and W depends on the path and are not the state functions. We follow sign conventions of Q and W by giving the position sign to these quantities when these are added to the system. We can measure the transfer of heat from one system to another, which causes the change in temperature. The magnitude of rise in temperature depends on the heat capacity of a substance. Therefore, heat absorbed or evolved as Q is equals to C delta T. Work can be measured by W minus is equals to minus Px delta V in case of expansion of gases. Under reversible processes, we can put Pex is equals to P for infinitesimal changes in the volume of making W reversible is equals to minus P delta V or dV. In this condition, we can use gas equation PV is equals to nRT. At constant volume, W is equals to 0, then delta U is equals to QV. Heat transfer at constant volume, but in a study of chemical reaction, we usually have constant pressure. We define another state function enthalpy. Enthalpy change delta H is equals to delta U plus delta NGRT can be found directly from the heat changes at constant pressure. delta H is equals to QP, where the varieties of enthalpy changes, changes of phases such as melting, vaporization, and sublimation usually occur at constant temperature and can be characterized by enthalpy changes which are always positive. Enthalpy of formation, combustion, and other enthalpy changes can be calculated using Hess Law. Enthalpy change for chemical reactions can be determined by delta RH is equals to summation AI delta FH products minus summation BI delta FH reactions or reactants, I think. And in gaseous state, delta RH is equals to summation bond enthalpies of the reactants minus summation of bond enthalpies of the products. First law of thermodynamics does not guide us about the direction of chemical reaction, that is what is the driving force of a chemical reaction. For isolated system, delta U is equals to 0. We define another state functions S entropy for this purpose. Entropy is a measure of disorder or randomness for a spontaneous change. Total entropy change is positive. Therefore, an isolated system delta U is equals to 0, delta S is greater than 0. So, entropy change distinguishes a spontaneous change while energy change does not. Entropy change can be measured by the equation delta S is equals to Q reversible upon T for a reversible process. Q reversible T is an independent of path. Chemical reactions are generally carried at constant pressure, so we define another state function gives energy G, which is related to entropy and enthalpy changes of the system by the equation. Delta Rg is equals to delta Rh minus T delta Rs. For a spontaneous change, delta G system is less than 0 and at equilibrium, delta G system is equals to 0. The standard Gibbs energy change is related to equilibrium constant by delta Rg is equals to minus RT ln K. K can be calculated from this equation if we know delta Rg, which can be found from delta Rg is equals to delta Rh minus T delta S. Temperature is an important factor in the equation. Many reactions which are non-spontaneous at lower temperature are made spontaneous at higher temperature for systems having positive entropy of reaction. Chapter completed. I hope that this audiobook will help you in your exam. Share with your friends so that they will also get the benefit. ये बात मैं आपसे बार बार रिपीट करती हूँ बच्चों, इसको ज्यादा से ज्यादा शेयर करिए क्योंकि अभी बहुत सारे बच्चों को नहीं मालूम है कि इस तरह की ऑडियो बुक्स भी अवेलेबल हैं. मेरे पास में बहुत सारे बच्चों के ऐसे कमेंट्स आते हैं कि उन्हें अभी तक ये पता ही नहीं था कि उनके पास में एनसीईआरटी ऑडियो बुक्स भी हैं. सो आप लोग इसको ज्यादा से ज्यादा शेयर करेंगे तभी लोगों को पता चल पाएगा कि हाँ एक चैनल एग्जिस्ट करता है जिसमें इस तरह की ऑडियो बुक्स भी अवेलेबल हैं. सो एवरीथिंग डिपेंड्स ऑन यू एवरीवन. So take care everyone. See you soon in the next video. कल मॉर्निंग में मैं केमिकल काइनेटिक्स का पार्ट 2 अपलोड करूंगी. So we'll see you in the next video. Till then, just stay tuned with me. Take care. Bye bye.